All right, let's talk about something that feels like it's pulled straight from science fiction. You know that spooky action at a distance that Einstein talked about? It paints this picture of a perfect, instantaneous connection between two places, no matter how far apart they are. And that, of course, leads to one very, very tempting question.
So let's run a little thought experiment. Imagine two people, Alice and Bob. They each have a quantum computer, and these computers share a special entangled link. Now, if Alice changes a file on her end, does that change just magically appear on Bob's computer at the exact same moment? It's a killer idea, right? Our own cosmic zero-lag internet. But is it possible? The short answer, a big, fat no. And I know, that probably feels like a huge letdown, but stick with me here because understanding why the answer is no is honestly way more incredible than if it were yes. It's the key to unlocking how the quantum world really works and what it can really do.
So let's get into the universe's ultimate speed limit. This isn't about ruining our sci-fi dreams, I promise. It's about figuring out why that spooky action is so much more subtle and frankly so much more powerful than a simple instant messaging service. And it all comes down to one fundamental cosmic rule.
And this is that rule, the no communication theorem. It is a bedrock principle in physics. And what it says, basically, is that even though entanglement creates this amazing, perfect correlation, you can't use it by itself to send a brand new message. Alice can't just wiggle her particle to make Bob spell out, hello. To really get why, we need a good analogy. Okay, picture this. Imagine Alice and Bob have a super long tape filled with random coin flips. But here's the trick. Their tapes are perfectly correlated. So if Alice looks at her first coin and sees heads, she knows with absolute 100% certainty that Bob's first coin is also heads. But, and this is the whole game right here, Bob doesn't know that. All he sees when he looks at his coin is a random flip.
And that quote just nails it. The outcomes are connected for sure, but to each person, they just look random. Think of it like this. Entanglement gives Alice and Bob a shared secret codebook, but it doesn't give them a phone to actually talk to each other. They share the same random data, but they can't use it to transmit new information without, a regular old phone call.
So let's break that down for our file editing scenario. When Alice measures her qubit, edits the file, the result she gets is completely random, a 50-50 shot. Now, from Bob's point of view, his qubit is also completely random. Yeah, their results are linked, but Bob has no way of knowing what Alice saw, or even that she did anything at all, until she sends him a regular, old-fashioned, slower-than-light message. That classical message is what unlocks the whole thing.
Okay, so if entanglement isn't an instant messenger, then what is all the fuss about? Why are we spending billions of dollars on this stuff? Well, this is where it gets really, really cool. Because when you combine entanglement with a little bit of classical communication, you unlock this entire toolbox of abilities that are, well, they're mind-bending, and they're totally impossible in our normal, everyday world. Let's start with a big one.
Teleportation. The word alone gets you thinking, beam me up, Scotty, right? Dematerializing and rematerializing somewhere else. Quantum teleportation is different, but it is no less amazing. It's not about moving matter. It's about moving the pure, fragile information, the exact quantum state of a particle from one place to another. And in the process, the original is destroyed.
Now, this circuit diagram might look a little intense, but you only need to focus on one detail. See those lines in the middle? That's the classical channel. That's the part where Alice has to send her measurement results to Bob. It's the critical piece of the puzzle, and it proves that without that regular, non-instant message, the whole process just grinds to a halt.
So let's walk through it. How does it work? First, Alice and Bob share an entangled pair. Got it? Second, Alice takes the particle she wants to send and measures it together with her half of the entangled pair. Third, and here's the part that obeys the speed of light, she sends the results of that measurement, just two classical bits of info, over to Bob. And finally, Bob uses those two bits like an instruction manual to tweak his particle. And boom! The original quantum state is reborn in his lab.
So, entanglement can help us move quantum information around. That's incredible. But its properties also let us do something that might be even more important: securing our classical information in a way that is literally guaranteed by the laws of physics themselves. What you're looking at here is a process called quantum key distribution, or QKD. Don't worry about the nitty-gritty details. The core idea is simple. Alice is sending single particles of light, photons, to Bob.
And their goal is to use the quantum weirdness of these photons to build a secret encryption key, knowing with absolute certainty that nobody else is listening in. So what's the security guarantee? Well, it's a beautiful, fundamental rule of quantum mechanics. You cannot measure something without changing it. So if an eavesdropper, we'll call her Eve, tries to intercept those photons, she can't help but leave behind evidence. It's like leaving footprints in the snow. Alice and Bob can just check a small sample of their data, and if they see any errors, they know Eve was there. They just toss out the key and start again. It's basically unhackable. All right, so we have these amazing tools like teleportation and QKD, but that's all just point to point. How do we scale this up? How do we connect labs and cities and countries? This is the grand challenge of building the quantum internet, and it's all about stitching these smaller links together.
To do that, we need another technique that sounds completely impossible. It's called entanglement swapping. Get this. Imagine Alice is entangled with a guy in the middle, Charlie, and Bob is also entangled with Charlie. If Charlie does a very specific measurement on his two particles, he can actually create a new entanglement link directly between Alice and Bob, even though their particles have never ever interacted before. It's like teleporting the entanglement itself.
And that incredible trick, entanglement swapping, is the engine that powers the next crucial piece of hardware, quantum repeaters. See, in the normal internet, if a signal gets weak, you just amplify it, but you can't copy a quantum state. So instead, quantum repeaters use entanglement swapping again and again to stitch together lots of short, fragile links into one long, high-quality, coast-to-coast connection. These are the absolute backbone of a future quantum internet.
So how far along are we? Is this all just theory? No way. Right now, today, there are small-scale networks linking a few nodes in different cities. There are satellites in orbit beaming down quantum keys. The goal for the next decade? To use those quantum repeaters to build the first state-to-state networks. And the long-term vision? A global quantum internet connecting quantum computers and users all over the world. Okay, we have covered a ton of ground. We started with a pretty simple sci-fi idea, and we've ended up with the actual blueprint for a brand new kind of internet. So let's just take a breath and bring it all together and really see how we've moved from a popular myth to the mind-blowing reality of what entanglement can actually do.
Let's go all the way back to the beginning. That idea we started with. Alice edits her file, and it instantly syncs for Bob. After everything we've talked about, is that dream truly dead? Well, in that magical, faster-than-light form, yeah, it is. But that is absolutely not the end of the story. Because here's the real takeaway. The truth is so much better than the fiction. The myth was this idea of instant, passive data syncing, but the reality gives us real, powerful tools to work with. It gives us communication that is physically, fundamentally unhackable. It gives us the power to teleport quantum information from one place to another, and it's giving us the building blocks for a revolutionary quantum internet, a network built not on breaking the laws of physics, but on using them in the most ingenious ways possible.
So I'll leave you with this final thought. For all of human history, we've protected our information with clever locks and complex math. But quantum mechanics offers something new. It offers security and communication that isn't just guaranteed by human cleverness, but by the fundamental laws of the universe. So the question isn't, can we send data instantly anymore? The real question is, what will we build when our most important information is protected by physics itself?